Okay, hello everyone. So let's continue the topics we were doing last time. So last time we defined the Ramsey numbers, capital R of R and S, the Ramsey numbers. And if you remember, we talked about, for example, R of 3 and 3. Let's say if you want to have any red-blue coloring of a complete graph to contain either a red triangle or a blue triangle. We saw that if we work with K5, there exists a red-blue coloring that contains no red triangle or blue triangle. So that means n equals 5 is not big enough, but if we increase it to n equals 6, then any red-blue coloring of K6 contains either a red triangle or blue triangle. Okay, so let me write this as a remark. If for a given integer n, the complete graph Kn has the property that any red-blue coloring of Kn contains either a red click of size R or a blue click of size S, then what can we say? Well, if I want to compare capital R of R and S with this n, my assumption is that I have a value of n such that any red-blue coloring of Kn has either a red click of size R or blue click of size S. Now, capital R of R and S is defined to be the smallest integer n that has this property. So if I have some Kn that has this property, that means that capital R of R and S has to be less than or equal to this value of n. Because capital R of R and S is defined to be the smallest value of n that has this property, and my assumption is that I have some Kn that has this property. So that means capital R of R and S is less than or equal to n. And conversely, the converse is also true, meaning that if I have a value of n bigger than or equal to capital R of R and S, then any red-blue coloring of Kn has either red click of size R or blue click of size S. Because if you call, for example, capital R of R and S as small m, then Km is the induced subgraph of Kn. And we know that in Km, the smaller one has either red click of size R or blue click of size S. And that itself is a subgraph of Kn. So Kn definitely also has the same property. Okay, this is one remark. Another remark is that if for a given value of n, Kn, capital Kn has the property that there exists a red-blue coloring of Kn that has no monochromatic clique of size R over S, then capital R of R and S has to be bigger than N. If for a fixed Kn, there exists a red-blue coloring of fixed Kn that has no monochromatic clique of size R or S, so that means no red clique of size R or blue clique of size S, then that means that value of N is not big enough. In order to have capital R of R and S, we have to consider an integer such that Kn for that integer has the property that any red-blue coloring of it has either red clique or size blue clique of size R or S, right? So think about R of 3 and 3. When we consider K5, it was not big enough in order to have a guarantee that any red-blue coloring of it has either red triangle or blue triangle, because we presented a specific coloring of K5 that had no triangle of same color, no monochromatic triangle. So that means R of 3 and 3 cannot be 5. We have to go bigger than 5. And then we saw 6 is big enough. Okay, so these two remarks are important and we are going to use them. Now, last time we wanted to prove the theorem that was saying that capital R of R and S exists for every R and S, and there is a specific upper bound for it, which is R plus S minus 2 choose R minus 1, which is same as R plus S minus 2 choose S minus 1. And to prove this, we saw that we needed to prove following lemma first. The lemma is saying that for R and S bigger than or equal to 2, capital R of R and S is less than or equal to capital R of R minus 1 and S plus capital R of R and S minus 1. Okay, now let's prove this proof of lemma. Okay, so let me consider a complete graph of size n equals capital R of R minus 1 and S plus capital R of R and S minus 1. We will show that any red-blue coloring of Kn contains a red clique of size R or a blue clique of size S. Okay, and then if I show this, what can I conclude? Let's think about remark 1 we said here. We said if there exists an n for a specific value of n, Kn has the property that any red-blue coloring of it has either red clique of size R or blue clique of size S, then we can say that capital R of R and S is less than or equal to n, because capital R of R and S is the smallest integer n having this property. So if I show this Then by remark one above, we can conclude that capital R of R and S is less than or equal to n, which is capital R of R minus 1 and S, plus capital R of R and S minus 1. Okay, so it's left to prove that any red-blue coloring of Kn has red clique of size R or blue clique of size S. So to prove any red-blue coloring of Kn has red clique of size R, blue clique of size S, consider a red-blue, consider it to say an arbitrary red-blue coloring of Kn, and fix a vertex V, or you could say V naught. Fix a vector V naught, okay? So this is one vector, one vertex of n vertices that we have in total, okay? So then we are going to partition. So this is V naught belongs to V, which is, for example, V naught, V1, all the way to Vn minus 1. Okay, now partition V into two sets, or if you say three sets. So V, we're going to write as M union N union V naught. So how do we partition V where every edge between V naught and elements of M are or is red, and every edge between V naught and elements of N is blue. Okay, this is a complete graph. And I'm fixing one vertex here. So there is an edge between this vertex and every other vertex of this graph. And so how many edges do we have from V naught to the other vertices? So they're going to be n minus 1 edges. Now each of these edges is either blue or red. So the ones that are red, there is for each red edge one endpoint is V naught, the other endpoint is some VI, right? So put all those VIs in the set M. And similarly, put all the points Vj where there are endpoints of blue edges, put them in N. And then I have a partition of my vertices. Okay, so let me draw a picture for you here. See, this is, for example, V naught. Okay, there are some red edges and some blue edges. You see, this one, let's call it VI1, VI2, VI3, VI4, These are elements of M. I'm going to put them in M. And then there are some vertices here. The vertices have no color themselves, so we draw them with black. And then I have VJ1. I'm going to put it in N. VJ2, put it in N. VJ3, put it in N. VJ4, put it in N, right? And so on. Okay, so thus we can write, what can we write? We can write that N, which is number of elements in V, right? Which is also R of R minus 1 and S plus R of R and S minus 1. Remember, this is how we defined N. We said at the very beginning of the proof, we said that we're going to consider a complete graph of size N, which we defined it this way. So N is equal to number of elements of V, which is R of R minus 1 and S plus R of R and S minus 1. And is also equal to number of elements in M plus number of elements in N plus 1. Remember that V is partitioned with M union N union V naught. So any two of these sets are disjoint, and number of elements of V is number of elements of N plus number of elements in N plus 1. Okay, based on this, what can I say? Thus, I can say that number of elements of M is bigger than or equal to R of R minus 1 and S, or number of elements of N is bigger than or equal to R of R and S minus 1. Why can I say this? See, it's a very simple fact. I have addition of these two numbers equals addition of these three numbers. So I'm saying that this number is bigger than or equal to this number is bigger than or equal to this, or this number is bigger than or equal to this. Why is that? Because if none of these happen, see, if not, M would be less than R of R minus 1, and N would be less than R of R and S minus 1. And then that would imply that M plus N, number of elements in N plus number of elements in N, will be less than or equal to, right? So if this is less than R minus R of R minus 1 and S, if number of elements of M is less than number of elements is less than capital R of R minus 1 and S, that means number of elements of M is less than or equal to capital R of R minus 1 and S minus 1, right? Remember, everything is here in integer. So if, for example, M is less than 5, that means M is less than or equal to 4, right? So that means this is less than or equal to capital R of R minus 1 and S minus 1 plus capital R of R and S minus 1 minus 1, which is capital R of R minus 1 and S plus capital R of R and S minus 1 minus 2. And then I have capital M, number of elements capital M plus number of elements capital M plus 1 has to be equal to this expression here, which could not happen if this happens, because then I would have capital M plus capital N plus 1 equals less than or equal to, I would have this less than or equal to capital R of R minus 1 and S plus capital R of R and S minus 1. Minus 2 plus 1 means minus 1, right? And this is contradiction with, so let me call this expression star. contradiction with star. Contradiction with star. Okay, and then that means that I have either n bigger than r minus 1 and s, capital R of r minus 1 and s, or capital N, number of elements of capital N bigger than or equal to capital R of r and s minus 1. Okay, now let's proceed. Now, okay, so first possibility, case 1, number of elements of M is bigger than or equal to capital R. The first possibility was number of elements of M is bigger than or equal to capital R of R minus 1 and S. Second possibility is number of elements of N is bigger than or equal to capital R of R and S minus 1. So if capital M is bigger than or equal to capital R of R minus 1 and S, okay, then K cardinality M includes either a red clique of size R minus 1 or a blue clique of size S by remark 1 above, right? Remark 1 was saying this, that if N is bigger than or equal to capital R of something, then Kn also includes a red clique of size R or blue clique of size S. So if latter happens, if latter occurs means what? Means if your Km has a blue clique of size S, then what does that mean? Then Km has a blue clique of size S, and so does the original graph Kn, because Km is used subgraph of Kn, right? Km is inside Kn. Kn is the complete graph of order n. Now Km is also a complete graph inside the original complete graph. Now if the complete graph inside has a blue clique of size S, the original bigger complete graph must also have a blue clique of size S, and we are done. Because what was our goal? Our goal was to show that our original graph, complete graph Kn, has either a red clique of size R or blue clique of size S. So now we will be done in this case. Okay. Now, if former occurs, two possibilities. Km either has a red clique of size R minus 1 or blue clique of size S. Blue clique of size S, then we are done. If it has red clique of size R minus 1, if former occurs, then K cardinality M has a red clique of size R minus 1. Okay. But I'm looking for a red clique of size R. How can I find the red clique of size R? Okay, so let me remind you about the situation that we had. So we have V naught here, so one fixed vertex, and then all elements of M are the vertices where the edges corresponding to them are red. So it could be something like this, you know. And say this is V. Okay, let me give this a name. We have a red click of size R minus 1. Let me give it a name, say S equals VI1 to VIR minus 1. Okay, so we have some vertices here. Now, see, each of these vertices is connected with a red edge to V naught, but the edges between these vertices could be red or blue in general. So let me give an example here. See, for example, let's say this could be red, for example, and let's say this is red, and let's say this is red, but then let's say this one is blue, and let's say this one is blue, right? So, and let's say this one is again red. So it's all possible that the edges between themselves could be red or blue, but my assumption is that I have a click of size R minus 1. Once I have a click here, red click, once I know that I have a red click, let's say this is my red click here. Let me show you with the arrow here, with the cursor. So this is a red click. Okay, so I called it VI1 to VIR minus 1. So let's say this is my VI1 here. Let's say this is VI2, and let's say this is VI3. Okay, once I know I have a red click, so VI1, VI2, VI3 here, once I add V naught to it, I will still have a red click of size 1 more than the previous one. Why is that? Because V naught is connected with red edge to each of these VIs, to each of the elements in M, and these are all elements in M. So I know that by assumption there are red edges between these VIs, and to V naught they're all connected with a red edge by definition of capital M. So I will still have a red click of size 1 more than previous one. So here let me say figure for let's say R minus 1 equals 3, which means R equals 4. So this is the figure, and we have a S, which is red click of size R minus 1. Then by definition of M, S, so as explained just right before, so S union V naught is a red click of size R minus 1 was size of S, plus 1 is size of the set V naught, which is R. So we found a red click of size R in our K, red blue coloring of K. That's it. So we are done. So we said we considered 2 cases. One case we had blue click of size S, then we were done. Another case, we had red click of size r minus 1. We added one vertex to it, the proper vertex to it. Again, we got a red click of size r. Again, we are done. So this was case 1 if number of elements in M is bigger than or equal to capital R of R minus 1 and S. So of course, you know, by symmetry, the other case is similar. So case 2, and bigger than or equal to R and S minus 1, similar to case 1. Okay, so we are done. Okay, so we proved the lemma. Now, using this lemma, we prove the theorem above, which means that we want to prove that R of R and S is less than or equal to R plus S minus 2, choose R minus 1, which is same as R plus S minus 2, choose S minus 1. So the proof of this one is by induction. The proof is by induction on R plus S. Okay, so first R plus S. So remember R and S, each one are greater than or equal to 1. So for R equals S, and R plus S is 2, and that happens only if R and S are both 1. So for R plus S equals 2, i.e. R equals S equals 1. What can we say? R of 1 and 1. So what is this? This is 1, right? Complete graph of size 1. So we just need one vertex. And this is same as 1 plus 1 minus 2, 1 minus 1. It is 1. Okay. So next, suppose let's say R of R and S is less than or equal to R plus S minus 2, choose R minus 1. For R plus S less than or equal to K. And we have to prove it for R plus, so now for consider, let's say R prime and S prime with R prime plus S prime plus K plus 1. Okay, so then we can say that R of R prime and S prime by lemma is less than or equal to R of R prime minus 1 and S plus R of R prime and S prime minus 1. Now, this is less than or equal to by induction assumption. This is less than or equal to R prime plus S prime minus 1. Choose R prime minus 1 plus R prime plus S prime minus minus 1 minus 2, right? Choose R prime minus 1 minus 1, R prime plus S prime minus 1 minus 2. choose r prime minus 1. So here, because r prime plus s prime minus 1 is less than equal to k. So see, r prime plus s prime is k plus 1. That means r prime plus s prime minus k is less than equal to k, but I am assuming that for r and s satisfying r plus s less than equal to k, I have capital R of r and s less than equal to this number. Okay, so r plus s minus 2, choose r minus 1. So I'm applying it for r prime minus 1 and s. So r prime minus 1 plus s prime minus 2, choose r prime minus 1 minus 1. And this one, r prime plus s prime minus 1 minus 2, choose r prime minus 1. So how much is this? Let's simplify this. So this is r prime plus s prime minus 3, choose r prime minus 2, plus r prime plus s prime minus 3, choose r prime minus 1. And this is same as r prime plus s prime minus 2, choose r prime minus 1, using, so we have a famous identity for binomial coefficients, which is n choose k minus 1 plus n choose k, right? Is equal to n plus 1 choose k. So this is our n here, choose k minus 1 plus n choose k. So that will be n plus 1, this is n plus 1, choose k. So we proved capital R of r prime and s prime less than equal to r prime plus s prime minus 2, choose r prime minus 1, which is exactly what we wanted. Okay, now an immediate conclusion of this is that capital R of R and R, so basically this is called diagonal Ramsey number, because you know R and S are both equal to each other. So we're looking at the diagonal. Capital R of R and R is less than equal to R plus R minus 2, choose R minus 1, which is 2R minus 2, choose R minus 1. So how do you think we can bound this number? I want to bound this by an exponential function. So my claim basically is that less than equal to 4 to power r over root r. So if I prove this, then that means the Ramsey numbers have an exponential upper bound. So proof of this, we need to prove 2r minus 2, and choose r minus 1 is less than equal to 4 to power r over root r. i.e. need to prove, so if I call r minus 1, let's call it n, then I need to prove 2n, choose n is less than or equal to 4 to power n plus 1 divided by root n plus 1 for n bigger than equal to 0. Okay, let's consider 2n choose n. Note 2n choose n. What is this? This is 2n factorial divided by n factorial, 2n factorial divided by n factorial to power 2. So to bound this, I'm going to use Stirling formula. Bound this, use the Stirling formula, which says that the inequality version of Stirling formula says that n factorial is less than or equal to root 2 pi n to power n plus 1/2 e to power minus n plus 1 over 12n, and that's a strict inequality, and bigger than root 2 pi n to power n plus 1/2 e to power minus n plus 1 over 12n plus 1. Okay, so this is a standard Stirling formula. Of course, it's not as famous as the other formula, which gives the asymptotic behavior of n factorial. But this one is also a standard version, the inequality version. Now, based on this, I can say that n factorial is bigger than, right, root 2 pi n to power n plus 1/2 e to power minus n. Because this itself, if I delete 1 over 12n plus 1, then I get something smaller. So n factorial is bigger than this. And that means n factorial over 2 is bigger than 2 pi n to power 2n plus 1 e to power minus 2n. Also, so what can I say about 2n factorial? So if I replace n with 2n here, let me call this one star. Also, by replacing n with 2n in star, what do we get? We get 2n factorial. 2n factorial is less than root 2 pi. Then 2n, I'm replacing n with 2n, so 2n to power 2n plus 1/2 e to power minus 2n plus 1 over 12 times 2n. Okay, so I want to assume that n has to be, okay, n has to be greater than or equal to 0 in this version, but we can consider n equal to 0 separately. So let me assume that n is bigger than or equal to 1 here. So this is less than root 2 pi, 2n to power 2n plus 1/2 e to power minus 2n plus 1 over 24, assuming n is bigger than or equal to 1. Okay, so so what can I say then? So hence 2n, choose n, which was 2n factorial over n factorial squared is going to be less than. So if I write the upper bound for numerator, lower bound for denominator, of course I'll get an upper bound for this fraction. So 2n factorial is less than, where was it? 2n factorial is here, root 2 pi, 2n to power 2n, 2n to power 2n plus 1 half, e to power minus 2n plus 1 over 24, and then divided by lower bound for n factorial squared is 2 pi to power times n to power 2n plus 1 e to power minus 2n. Okay, so now let's simplify things. See what happens. Root 2 power 2 pi is 1 over root 2 pi. And then I will have 2n to power 2n. So that's 2 to power 2n. I can write as 2 to power 2n, which is 4 to power n. 4 to power n. And then n to power 2n cancels with n to power 2n. I will have 2 to power 1 half. So that means 2 to power 1 half. And I will also have over n to power 1 half here, right? Because this is 2n plus 1, n to power 1. But I have here n to power 1 half. E to power minus 2n cancels with e to power minus 2n. I also have e to power 1 over 24. So this is going to be e to power 1 over 24 over root pi. Root 2 cancels with root 2. 4 to power n over root n. Okay. And e to power 1 over 24 over root pi, you can check that is less than 1. So this is less than 4 to power n over root n. So we proved that 2n choose n is less than 4 to power n over root n for n bigger than or equal to 1. Okay, so this means that 2 times n plus 1, choose n plus 1 is less than 4 to power n plus 1 over root n plus 1 for n bigger than or equal to 0. Lastly, to complete the proof of, so if you remember, our goal was to prove this. So let me call this one, let's say 2 star. So we already proved that 2n plus 2, choose n plus 1 is less than this quantity that we want. We want to show that 2n choose n is less than this quantity. So in order to complete the proof of 2 star is enough to show that 2n choose n is less than or equal to 2n plus 2 choose n plus 1. Because if we show this, 2n choose n is less than this, and this itself, 2n plus 2 choose n plus 1 is itself less than 4 to the power n plus 1 over root n plus 1, and that will imply, combining this to imply that 2n choose n is less than 4 to the power n plus 1 over root n plus 1, which is exactly what we needed to prove. And this is easy to verify. To verify this, 2n plus 2 choose n plus 1 divided by 2n choose n. So this is going to be 2n plus 2 times 2n plus 1, right? If you simplify factorials, divided by n plus 1 the whole squared is 2n plus 2 over n plus 1 times 2n plus 1 over n plus 1, and is obviously bigger than 1. And this completes the proof. Okay, so we showed the upper bound for Ramsey numbers, diagonal Ramsey numbers basically. Capital R of R is 4 to power R over root R. So next time we will show that the lower bound is also exponential. Okay, so this would imply, which would imply that capital R of R and R grows exponentially. Okay, however, the base that grows exponentially, but with which base? The base is still unknown. Okay, so Ramsey numbers, these mysterious Ramsey numbers, they exist and are finite, and they grow exponentially because upper bound and lower bound, we just prove upper bound is exponential. Next time we'll prove lower bound is exponential using probabilistic methods. So we'll start probabilistic methods next time. We'll give you like a brief introduction to probability theory, just the amount that we need for now. And then we will dig into this probabilistic method, and we use it to show the lower bound is also exponential. So that means Ramsey numbers grow exponentially, but which base? Still open problem. Okay, so see you next time. Thank you.